All right, our final assessment in this little section on matrices was about writing our row operations as matrices that we could do matrix multiplication with. So first and foremost, they said let A be any 4 by 4 matrix. So they're just saying, hey, we have a 4 by 4 matrix that we want to manipulate. Let's discover what those things would be. First thing it said was let's create a matrix M that could be used to just swap row 4 and row 1. And we know if we want to get this matrix M, what we're going to do is we're going to take the original identity matrix and we're going to do a row 1 and a row 4 swap. Now, I'm not even going to write that out. Most of us who got in trouble on this one was mostly communication. We are finding M, so M is equal to. A lot of students wrote like M right next to the matrix, like it looked like it was multiplying. It was very confusing, but we're finding a 4 by 4 matrix. We're going to take our original identity matrix and just go ahead and multiply, swap rows 1 and row 4. So that would look like this. Row 2 and row 3 stay the same, and we're done. Now, because we didn't spend a lot of time demoing this in class, I'm going to take a moment to demo what this looks like. So I'm going to just go ahead and multiply this. This is not part of the answer. I'm going to have deep regrets, but it's fine. I'm just going to write the alphabet. I'm going to show what this matrix multiplication does, right? Why it's doing this. So if we actually go through and do our matrix multiplication, right? So the very first row, we're going to go down this column. I'm going to have nothing to add, 0 A's, 0 E's, 0 I's as I'm doing this inner product, and a single M. And I'm going to go down the next column. Same thing's going to happen, right? 0 B's, 0 F's, 0 J's, and I'm going to get a single N. And it's going to happen all the way down, right? And then we can do the same thing. The next one, I'm going to get, let's just do this second element. 0 B's, we're in this column, this row now. 0 B's, 1 F, 0 J's, and 0 N's. And so you can see that we're going to end up, everything here is going to stay the same. Demonstrate this to yourself. And then that last row, as I go down that, now when I do that first column, that first inner product, I have a single A and then everything else is zeroed out. When I move over, I'll have a single B, everything else will be zeroed out, C and D. And so we can see that resulting swap. Now, right now, I just want to point out, I'm going to erase all this so I'm not going to be in trouble. I have a lie. I have M is equal to this multiplication. M is not equal to this multiplication. If I wanted to write this, I would need to write MA to let you know I am doing multiplication. So one of those moments where that equal sign is incorrect, but that's because I'm going to erase all of this. This was me just convincing you that that adjustment, right, that row operation performed to the identity matrix does actually result in a matrix that if we do multiplication, will do that row operation. All right, so let's just jump ahead. Q is then equal to row 1 plus row 2 ends up looking like this in the identity matrix. Everything else stays the same. We're only manipulating row 1 with this row operation. Cute. A lot of folks had a minus there for some reason, a -2. I'm not sure why we thought that would need to be negative. Maybe you were thinking like what it would have to look like for this to then become. I don't know. The goal here is to do a multiplication so that, again, I'll just do the first row, A, B, C, D, because that's all I need for this, right? I should have left it. I think it was this. As I do this multiplication, what's going to happen is I'll get 1A plus 2E. And then I move over, I'll have 1B plus 2F, right? That's the whole goal, is that I'm adding 2 of the row below to this row. Now I could do that just doing the row operation, right? Like that's going to be C plus 2G and D plus 2H. But the matrix multiplication will perform that for us. And then we saw there's a lovely relationship between all of these row operations, this matrix multiplication, and our determinants. That's pretty sick. So this is sort of where we're headed and why we're going there. But okay. And then P, again, we had a lot of people doing the inverse of this. I think we just we didn't take any time in class to multiply these and actually see what was happening. So maybe next semester I will make sure I do that. But in this case, we want to scale row 4 by 4. We're just going to go ahead. Only row that's changing is row 4, and we're just going to scale it by 4 for our identity matrix. Perfect. All right, the last piece here was, okay, how would we use this with A to show what those operations were? Some people walked me through the operations. That's not what this question is asking. This question is rewrite the operations as matrix multiplication. So we know matrix multiplication is going to start from the right-hand side, right, and move left. Honestly, it doesn't matter, but like with this vector, this is what we want to do, right? Especially if we're applying this to something. So the first thing we want to apply to A is this adding a scalar multiple of another row. And that was my Q matrix, right? That was what Q did. Then we want to scale up row 4, which is what P did. And finally, we want to do that row swap, which is what M did. So these are all going to happen to A in that order. So if I want the first thing to happen to A to be the row swap, I need to go ahead and do Q times A. Not the row swap, the addition of a scalar multiple of another row, right? That's going to go ahead and do that first because this is the first thing that would happen. And then I can be like, okay, next I want us to scale up row 4. And then lastly, let's do the swap. So this is our matrix multiplication. Doesn't matter in terms of the associative property, which multiplication we do first, but it does matter what order these multiplications are written in. So we needed to have this as our answer. Any other variation would not have worked here. And of course, you could actually write out the matrices, but that was just a lot more work to do that. So yeah, the idea here is, again, if we're doing something like determinants, like we just saw in the last section, we could talk about the determinant of this new matrix, right, compared to the original, and we'd be able to be like, okay, Q doesn't change anything, P is going to scale it by 2, and we do have that swap of M, so this would be a -2 determinant of A is the determinant of M, P, Q, A, right? So that's just like, these are the kind of the reasons that we're thinking about this. The order doesn't matter for that determinant nonsense. We talked about that, but it would matter in terms of what's going to happen to that resulting matrix. Because we know if we did a addition of a scalar multiple of another row before or after a swap, it would completely change what we were doing.